All right, line A6, we're going to be on to learning task 4D for Delta over here. We are going to get to the end of this transistors unit. We left off right about here, which was going to be where we start to use a transistor inside of an AC component. AC amplification is a huge deal for us, where we are going to go and take a really small AC signal, and then we are going to go and create a larger AC signal. But we need to be able to do so with an electronic device that's going to be DC powered. Now, if you're at all familiar with most of your handheld electronics, you understand that they operate off a battery. That is a DC supply. So there has to be a way that we can take something that is DC supplied and create some AC, because so much of what's happening is AC. Right now, my sound waves that I'm creating creating these sound waves with my mouth, my vocal cords and stuff like that. Those things are bouncing into my microphone. My microphone is then going to go and, store that, or not my microphone, but my computer stores them, records them, etc. And then they get played out to you. It is all happening on a DC device, but it is going to be an AC overlay that we are seeing. Over here, we've got an amplification circuit that has got a couple of capacitors in it. I want to just talk about those capacitors for a second. And then we're going to go and briefly describe them in short form, and we're going to go and technically describe them, what exactly they're doing, so you understand their application side of here. But before I look at those, what I want to do is I want to just go and take a look at the circuit without them inside of there. Okay, so I'm just going to go erase this one here, and then I'm going to go and erase this section over here. What do we have? We have got just a standard transistor type of circuit. A couple of things that we should know about this transistor circuit. We know that for certain, we are going to go and have a voltage drop of 0.7 volts. That's going to be across here, which means that we're going to be dropping the rest of whatever my voltage was over here across that, whatever it is minus 0.7. We also know that we are going to go and have some voltage that is going to be dropped across these components based upon the amount of continuous current that I am letting through this path. Whatever current is traveling through this path is going to go and establish my volts. V equals I times R. So whatever has been placed inside of there is going to go and give us a voltage drop that we would have over top of here. This is probably going to be biased for midpoint, whatever my voltage is. If this thing is going to be a 24 volt supply, this point over here is going to be biased for the middle of that. We'll call that 12 volts, because that's going to go and give me the maximum amount of overrun towards the top or underrun towards the bottom that I'm going to be able to go and have. This value over here, by the way, this 0.7, is not going to be always, the value down to the negative. In a lot of cases, in actual electronic circuits, this is a super simplified one over here, so just a baby circuit. But if we were doing actual hardcore electronic circuits, we would have a bunch of different resistances. We would go and have what's referred to as a stiff voltage divider, where we'd have another one over here and all this other stuff, so that we could actually bring this thing up a little bit higher than that 0.7 as well. But we'll work with the 0.7 because it's all we really need at this point. All right, I'm going to erase all of my white out here. We're going to take all this stuff back into here, and we're going to say, do any of these values change? Do I still have current that is going to be traveling through here? Absolutely I do. That current, emitted from here, is not going to go and try and cycle back through like that. Current doesn't do that. It does not return. It always looks for a spot that is going to be different. So we're not introducing any new paths that we're going to go and have. Same with this over here. That voltage drop is going to go and stay the same. What is going to happen to these caps inside of here? Well, what does a cap do in DC? It charges to whatever the value is going to go and be, right? Whatever we have, that cap is going to go and charge to. Let's take a look at what we have over here. Let's give this thing a value. We're going to say that it's a 24 volt supply and that we're going to be midpoint biased, which would mean that this point over here would be at a point of 12 volts. We need to understand this, that we see that 12 volts that we're going to have over there. If we go and have 12 volts there, that would mean that we also have 12 volts over top of this section over here. What is inside here? Well, it's a cap, and so if I've got a cap on DC is going to charge up to the value of voltage. Is this DC? You bet it is DC. So what's going to happen the first time that I turn this on is there's going to be a little bit of a pop. You've probably heard that before on mics and amps, when you plug or unplug stuff, that there's this popping noise. What you're hearing is an inrush. Literally, it is going to be an inrush that is just filling up a cap, and in doing so, it's just kind of popping a speaker out, or maybe sucking the speaker back towards the back end as well. It depends on what it is. But either way, it's this process of electrons that are going to go and tick, 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 tick. They're going to leave from there. They're going to flow through the speaker. The speaker is just an electromagnet that's going in and out, and they're going to go and start to build up here. As they build up on here, what happens? Well, we get an equal and opposite reaction on the other side of that cap, and we drive electrons away. Those electrons are going to go and leave. They're going to go up to my source over there. This is all going to go and happen until we reach out that value of 12 volts. Once we reach 12 volts, there's going to be no more current flow. That's going to be going to this cap. No more current flow. That's going to be running away. Whoa, running away from that cap as well. Let me go back and grab that one there. I don't know why it's being so incredibly stupid here right now. Whoa, it's all the way down in the lower corner. That's weird. And we will close that there. We'll go back to this. Clearly, it doesn't like something that I'm doing. I have no idea what. But back to where we were over here. Thankfully, we did not lose too much data. Bunch of electrons on this one over here. Bunch of holes on this side over here. It's going to be charged up to a value of 12 volts right now. There's no more current that is flowing through the speaker. That pop we heard when we first turned it on has happened. And now we're done. That's what's happened over here on this cap over here. What about on this one? Well, the instant that we powered this up, we would have had a current that would be established through here, like that. What is this? VBE, voltage from my base to emitter. You know this, 0.7 volts. If I take a look at this, I see that this circuit from here to here is in parallel with that 0.7 volts. So what is this cap going to do? It is going to go and charge to 0.7 volts. This is why we usually have that, stiff voltage divisor that I was talking about before, so we're able to pull it up a little bit higher because 0.7 doesn't give us a lot, but, we'll work with it in here. This 0.7, if I take a look, is going to go and be seen on here. So we're going to have electrons that are going to go and leave from here. They're going to travel through this microphone for a split second. The microphone is going to be a coil that we are able to bombard with sound waves, and as we do that, it's going to drive it in and out, which would generate a value of voltage and current. So we're just going to drive those electrons through here. The electrons are going to start to build up on here, driving away electrons on this side over here, and those electrons are going to go up through my source and back out. This is going to go and happen until we achieve a voltage of 0.7 of a volt. And once we achieve a value of 0.7 of a volt on there, then it is going to quit. Right? We're not going to get any more DC charging current. That's going to happen inside of here. I've got two caps that are charged up inside of here right now. This is what we refer to as the DC current flow. Transistors are AC and DC devices that are able to go and handle both of them at the same time. What we have now is a system that is going to go and have DC current continuously flowing through here. That is going to be my biasing current over there. DC current that is going to be continuously flowing through here. That is also going to be my input biasing. This is really my output biasing my collector. This over here is going to be considered to be my input biasing current. So those are going to be DC currents that are going to be flowing at all times. What happens when I drive sound waves towards this microphone? Well, when I go and drive sound waves towards this microphone is going to get pushed in. There's a little magnet on, our very basic microphones, a little magnet, little coil. We push that, the sound waves literally move the coil over top of the magnet and generates a very small amount of voltage. That is going to go and happen. Let's go and say that we generate a very small positive, negative voltage that we are going to go and have over here. Well, if this is going to be a positive over here, what is that going to go and do? That positive over there is then going to go and get counteracted. There's some negatives over here, so there's going to be a rush of electrons that are going to go whoosh off of that plate back towards this positive that we're creating. We're creating an electromagnetic positive. There's a little bit of a negative on the opposite side over there. Those are going to go and send electrons back out like that. The direction does not matter so much right now, what we are necessarily looking for. What it's doing is we're seeing that there's current that is being pulled back off of that microphone. It could have been in the opposite direction, which would have just added electrons onto it. But what we're seeing over here is that there's going to be a change. And as a result of that change, there's going to be a change in the amount of current that is going to go through here, because this voltage across here is going to change. It's going to go and become 0.7 plus whatever my microphone has over here. It's in parallel with it. So we're going to have more than 0.7 that's going to get impressed across here. That's why we actually need to go and have that other resistor that we're going to go and have on the bottom there that they don't show inside of here. But we can explain without it for now. It's going to increase the amount of volts that we would have over top. Once again, think about this thing as if it were a set of stacks. Over here, we're normally going to go and have my RB resistance of my base, and then we're going to have that 0.7. But over here, when we microphone this, we drive that up. That pushes this up over here. So we're moving that line up. When we move that line up, that means that this resistance of the base is going to have less volts dropped over top of it. Same value of resistance, it's still a resistor, but it's got less volts over top of it, therefore my current is going to go down. I is equal to E over top of R that we are going to go and see, right? So if I've got less volts over top of the same amount of resistance, I'm going to go and have less current. If I have got less current that is going through this path over here, what is that going to do on this side? Well, it's going to go and drop the amount of current that I'm going to go and have on this side over here as well. If I drop the amount of current that's going through here, that means that I am going to go and have less voltage drop that I'm going to go and have on this, right? V is equal to I times R. Current has gone down, therefore the voltage on that is going to have gone down as well. Now the voltage drop across there is going to go down, but you got to remember that this is a stack of voltage as well. We've got my VCE, collector to emitter, and we have got my VC, voltage dropped across my resistor in the collector over there. When we drop this, we're actually lifting this value over here, which means that as we lift this value over here, we are going to go and change the total amount of collector to emitter. This point over here moves from being at 12 volts where we had it before. It is then going to go up. It's going to become a little bit more positive. If it becomes more positive, remember that this cap and speaker are connected across that. So we're going to say that this goes from 12. We're going to go and increase it to, let's say, 14 volts over here. As we go and do so, that increase up to that 14 volts is going to go and result in us pulling more electrons through the speaker to go and charge that up to 14 volts, right? It's DC, it wants to charge up to that. So now we're going to go and get a rush of current through that speaker in that direction. And this rush is going to go and give us sound, right? It's going to go and cause that coil, the speaker coil itself, to go and move inside of it. That's where we're getting sound out on the other side. When this drops and, as a result, my current goes back to normal, this is going to go and drop back down. When this would drop back down from 14 over to 12, that would release. We would no longer be holding as many electrons, and so I'm going to go and have electrons that are going to go back through the speaker in the opposite direction. They're going to be released off of there and returned back to my source. What we're seeing over here is current traveling through that speaker in two separate directions. That current that is traveling in both of those directions is now going to be a actual AC waveform. So we can go and get a sound wave. If you've ever looked at, played with like vocal analyzers or anything like that, you can stick stuff through on your computer. I don't know. You remember early days of Windows Media Player, you could go and watch the waveforms and stuff like that. That was all really cool. We were really jazzed about that back in the day. But it is all going to be these waveforms that look like this. You've seen these things before. And because we're seeing those waveforms that are going up and down, we need to be able to go and replicate them in order to get intelligible sound out of there. That's what's happening inside of these. We go with a really simplified explanation. Now, this circuit is not without problems. This circuit is actually screwed for an amplifier because we can't vary the amount of volts over top of here. We do need to have a resistor in line with that for us to actually be able to go and do that, because this is always going to maintain 0.7, which would mean that we would need to have an additional amount of volts that we would go and drop off here. Ideally, what I would do with this circuit is I would bias, and this would be if I was actually building a technical one over here. Stick a resistor inside of there. I would go and bias this for a 24 volt system. This one over here, I would probably drop to 11 volts that I would have dropped across it. Then I'm going to go and drop 0.7 of a volt across this one, 0.7, which would mean that then I would be dropping across here the remainder, which would then become 12.3. Somewhere roughly around there is where I would aim to go and be at. That way, when my microphone takes noise in, it is going to go and either add to the electrons or pull away from the electrons here, which is going to go and either send electrons in or pull electrons in, right? If we would be pushing electrons onto this plate over here, that's going to go and send them out like that, which is going to go and increase this value of voltage over here. If I would be pulling them in or releasing them from here, then what I'm going to do is I'm going to be pulling more through that junction over there. So there's always going to be, this path where we're going to go and pull more in. If this is going down over here, I'm going to be pulling more in through here, and as a result of that, my current through this is also going to be going up, which means that my voltage over top of this would at that point be increasing, which would be pushing this level down. That is the proper way to go and look at it. The book is just missed that. You know, it should have had that resistor inside of there. For your intents and purposes, you need to recognize what the caps are doing at this point. We've gone over the fact that we can take DC and we can go and apply sound waves over top of it in this case, and then we're going to be able to amplify and pass those through. We're going to go and pass other stuff through as well. I have no idea what is going on over here with this, but it is really problematic right now. It's starting to drive me crazy. Yeah. But it's going to allow us to go and amplify these. We have this saying that we do use for caps. What we'll say, and you need to write this down, that a cap, capacitor, caps will pass AC but block DC. In other words, if I apply DC, it's going to charge up, and after that point, there's going to be no more current that is going to go and flow. It's going to block all DC current once it's charged. If there's AC, it is going to pass that AC current. In other words, we are going to go and see that AC, the effect, is going to be able to get passed through from one side to the other because we're going to get equal and opposite reactions always that are going to happen. So what we'll use caps for is we will use caps to go and prevent us from shorting out the DC sections. If I did not have these caps inside of here, what I would have is I would have this then. This is just a coil of wire inside of here. This would be a coil of wire on DC. How does an inductor act in DC? Well, it gives me 5 tau of opposition. After that, it steps out of the circuit. So in essence, if I did not have that cap inside of there, that microphone would act as if it were a short down to my negative over here. And if that would be shorted out over here at the negative, we wouldn't be able to get 0.7 volts, which would mean that my transistor would be shut off. That'd be if I was missing that one. If I was missing this one, same deal. It's going to go and act as if it were a short. We're going to bypass whatever this is trying to do over here, and we would go and have this thing that it would act as if there was a short going from there to there, and we would see all of our source voltage being dropped over top of that resistor. But by virtue of placing them inside here, they're going to go and charge up, and then they're going to go and do what we say, which is caps will pass the DC waveform, but they will block, or sorry, pass the AC waveform, but they will block the DC waveform. That's why we have capacitors on so many inputs, so many different devices, because the devices are operating on DC. Their amplification, all of this stuff is all DC inside of there, and we need to prevent that DC from being leaked down to ground, and that's why we've got the caps in there. Amplifier gain is going to be different for AC compared to my DC gain. DC gain is going to be the beta or the hybrid forward emitter, the HFE, that I'm going to go and have for a device. My AC gain is going to be just a basics of what's my voltage in compared to my voltage out. And it is not the same as your DC. You do need to go and make sure that if you are working with one of these systems, that DC gain that you're looking at is not placed as your AC. The only way to go and figure it out would be say, this is the amount of volts I'm getting out compared to this is the amount of volts that I'm getting in. And then you go and apply that formula, the V out, over top of the VN. Okay, Class A amplifiers. We've got 3 main types of amplifiers that we're going to have. We're going to have Class A, Class B, and Class C amplifiers that we are going to go and have. Class A is going to be the most common type of simple amplifier. It's a single amplifier over here that's going to be biased at its midpoint. We see that over here. We got 10 volts. We see that we're biasing this thing to be at 5 volts. By biasing it there to that 5 volts, we are then able to go and ride up. We can go up an additional 5 volts on our output over here, right? Get all the way up to 10 volts. We can drop an additional 5 volts down over here. And so for a even type of signal, I can go and get maximum amount of gain out of this thing. When we're looking at our waveforms, by the way, what we're going to go and see is that as far as current is concerned, we're going to get an inverted waveform. Over here, if I'm adding more volts to this that I'm going to go and have over here, and if this is charged up to a higher amount of volts than what we have over here. So I'm going to go and say this side over here, I'm going to attach it to something else. We can then go and charge, find the difference that we're going to go and have over here. So this, we're going to say, is brought to a value of like, we'll say 6 volts right now. We'll bring this thing up to 6 volts on this side. It's not the same as the previous circuit, because the previous circuit we were referencing down to ground. This one here is a powered circuit, so we're going to bring it to 6 volts. If we brought this to 6 volts, we would see that we would have a pile of electrons on one side and then we would go and have a bunch of holes on the other side. As soon as my input voltage would rise over here, that rise in input voltage would mean that I would have to go and store more electrons. So as a result, I'm going to get a rush, whoosh, of electrons through there. They're going to build up on here and drive more away over here. Well, when that happens, that's an increase of current that is going through from my base to emitter. That would mean that my collector to emitter current would also have to be increasing. And if my collector to emitter current is increasing, V is equal to I times R. That would mean that here's that increase of current. Therefore, the volts dropped over top of this are also going to go up. So this is now going to be dropping more volts. Before it was dropping 5 volts. Now we can say that maybe it's dropping, 6 volts or 7 volts. Let's say 7 volts. So let's say right now it's 7 volts. If it's dropping 7 volts, that would only leave us with, if we've got 10 volts here, that would only leave us with 3 volts that we would have over here. And so we see that it's an inverted waveform that we would go and have here. Same thing happens on this side. If we brought this thing back down to 6 volts, so then we've just got our regular DC biasing current going through there. We'll do that over here. We'll change that, change that, change that, and that. We've still got just a regular DC biasing current that is constantly flowing through here. This is why electronics take, phantom power. There's always a path going. But then if we go down below that, so from that 6 volts, we're going to drop that thing down to, let's say, 4 volts. As a result of that, we're no longer going to be holding as many electrons on here. So we're going to go and lose some electrons and holes. Where do those electrons go? Those electrons aren't going to go back towards the negative. They're going to go towards the positive. They're going to go up top over here. As they go up top over there, we're going to go and drop this value of voltage that we see over here, which means that we're also going to have less pull that we're going to go and get through that. As a result of that over here, me dropping the current that I'm going to go and have inside of here, that would mean that I'm going to drop the amount of current that I'm going to have inside of here. And if I drop the amount of current that I'm going to go and have inside of here, then once again, that is going to go and affect that value of voltage. So this voltage over here would then go down. Current goes down, voltage goes down, that I'm going to go and have. Well, if this voltage goes down, this was dropping 5 volts over here, this now turns to 3 volts, that would mean that we would have to be doing the makeup down here, 7 volts that we would have across here. And so I'm going to see an inverted waveform out there. Okay. That's the way that we go and take our signals, we pass them through. A class A is going to go and invert my signals as it moves over from one side to the other. It makes the signals much stronger. We're able to get bigger values out that are going to be more useful for us as electricians in our signals. Now, we're not looking to become audio amplifiers, and that's not what this is trying to be. This is trying to go and just pass AC signals, which we do a ton of in the field. Small AC signals that are going to be coming off of things like encoders or off of, positional sensors, temperature, humidity, all sorts of things like that are constantly changing. They're going up, they're going down. Think about temperature. It goes up, it goes down. Therefore, is it going to be an AC value? You bet it's going to be an AC value. So we have to be able to pass it through and make it stronger. Class B transistors, or Class B amplifiers, are going to go and use 2 transistors that are going to alternatively turn on and create different sides of my waveform. What we have on a biasing is going to go and determine whether or not we have got clipping on our signal. Clipping on a signal is going to basically mean that we've maxed out what we can go and get out of there. If I have got midpoint bias, that's what this is over here, 5 volts. I've got a total of 10 volts available to play with. I can go up 5 volts, I can go down 5 volts. But if I were to move my bias level, change the base resistance, things like that, if I were to bring that too low over here, I can amplify any top parts, but I cannot amplify any bottom parts. I just bottom out over there, so I get a clipped signal. It's always a kind of a distorted, weird audio sound. Same with if I bias this thing too high, I'm going to go and lose all the tops over here because ultimately I can't put out more than what I have over here, the 10 volts. I might dream of it on my transistor, but I'm limited by what I actually have available. It's just not a really good thing to go and get clipping. You're losing, signal itself. If every word I just, missed the first syllable of, obviously I would be unintelligible. I'm hardly intelligible as is, but it would just be a really, really bad thing to, add on top of that. So just watch out for that. The Class B transistors that are going to be alternately conducting are going to go and be inside of something like this, but they're going to go and be biased so that I can go and get a push out. This one's going to go and give me a maximum push out. This one's going to go and give me a maximum push back. Much more complicated circuits. Thankfully, we don't have to cover that for us as construction electricians. You just need to know that the B uses 2. Look at the B. The B itself has got 2 humps. Therefore, 2 transistors for you to go and remember that with. All right, that is the end of the transistor section. That has taken us probably, I don't know, far, far more time than what you probably anticipated when you sat down to read it, but it is a big section. You are going to need some of this theory, the basics of transistor amplification for next year when you are going to start looking at op amps. We're going to build from it. All right, cheers.